Hello world. So today we are going to talk about Nearest Neighbour, and I have decided to include in the computer vision playlist just to give a broader understanding of what you all need to do before starting off with image recognition and convolutional neural networks. So this video is meant to give you a broader understanding of what discrepancies are there when we use such an algorithm, and why you wanna not use linear classifiers on such dumb classifiers, because these are not at all useful when it comes to image recognition, and we are going to discuss why, and we are going to talk about what does it look like, and we are about distance metric which we use to compare two images, and then the problems which lie underneath this algorithm. So let's get into it. So image classifier, if you were to write an image classifier with hard coding, you will not be able to come up with an algorithm which classifies the image in a more accurate manner. I mean, if you were to write a Python function and you were to write a program which classifies the images or a set of images, it would not be apt to do that, because image recognition is just not about evaluation of pixels, but you all see all the features and you come up with boundaries, and it's just dumb to write an algorithm which does the process of image classification, because if you were to apply that classifier to another object, you would not be able to get the desired results which you want, because you have made several assumptions that the feature which you are using, feature which is there in this image, is gonna be there in that image, but you simply can't do that, because and so few attempts have been made while doing this. And let's see an example. Start with an example of cat. So in this, what we do is, you are gonna start off with boundaries, and then you're gonna focus upon features. As you deep dive into the features, you're gonna focus on the details. But since you are gonna write about only cat, your classifier is gonna fail on image recognition when it comes to different objects, and simply it's just waste of time writing classifier for a particular image. And what we are gonna do is we're gonna make use of data driven approach. So we make classifier. What classifier is consider it an algorithm which comes up with its own decision boundaries, just to classify whether that image belongs to this class or this class. And I've talked about multi-class classification in softmax, why softmax is used in the activation function, so feel free to check that out. And in this data driven approach, we make a classifier, then we feed that data set into the classifier, and then we're going to use machine learning algorithm, which is in this case Nearest Neighbour. And after training the classifier, we're gonna evaluate the classifier on a data set which we haven't seen across. And the main purpose is that we make use of test data set. In test data set, no, we don't know what data set that is all about. We haven't tested our classifier on that data set, because we want to check how our algorithm, how our model is going to perform on the data set which we haven't seen across. So if you were to apply that model onto some other purpose in real world, you're gonna come across data sets which is totally weird, and you wanna know how your data set is performing, because the main purpose is to test it out on those devices which have low computational power, and your classifier should work well, efficiently in testing time. So in Nearest Neighbour, what we do is we create two functions for train, and other one is predict. So in train, we memorize all the data sets, and in predict, we are gonna take information from the training set, and then we are gonna check and compare that image, test image, with the training image. I know it's dumb to compare two images with pixel-wise distribution, but this algorithm is so simple and so simple to interpret that you're gonna get a broad understanding of how neural networks are working. And so we're gonna predict the image of the most similar training image. And know that unlike deep learning, we are gonna need training set at the time of testing also, because it doesn't make any use of weights. It just Nearest Neighbour doesn't have any parameters which you can make use of. And we are gonna take example from this. So this dataset is of CIFAR 10, which is one of the most common datasets for training. And as you can see over here, we have 10 classes over here, 50,000 training images and 10,000 test images. And what our nearest neighbor algorithm is going to do is it's going to compare each image with its training image. So it sees the similarities and it computes the pixel wise distribution, which we are going to get back in the next slide. And as you can see over here, this is an image of a dog, and it sees all the features which are relevant, which are present in that dog picture, and it's going to compute pixel wise distribution, and using that metric distribution it's going to come up, suggest one nearest neighbor of this. And note that this nearest neighbor isn't much accurate, because as you can see over here, this picture over here looks like that of a deer, while the first picture is of dog, and it's not so robust and it's very brittle in this manner. And there are two distance metric which we use. One is called L1 distance and also called Manhattan distance, and other one is called L2 distance, also called Euclidean distance. And this metric is coordinate dependent, which we are gonna get back later, and it's gonna change when you change coordinates. So if you see the locus over here, you can see it like consider origin as a center of a square and then turn it around 90 degrees. So that's gonna be the locus, and I'll show you in the next slides. And so see over here, if our image is a 4x4 pixel image, like 4x4 column of pixels, and over the top left side if you see 56, and so if our test image has a pixel value of 56 and we are going to subtract that of a training image, element wise we are going to perform subtraction, and then we are going to take absolute difference. So we are going to get 456 in this manner. What we do is we compute pixel wise subtraction and then we take absolute modulus of it, so that we are only concerned with the values over here, we are not concerned with the signs. And then we take sum of the matrices and then we are going to come up with the values, and this is the metric which is being used when we saw this data set over here, which is being used to compare images. And so this is the code which we use for nearest neighbor classifier. We create a class over here, then we make this train function module which memorizes the data. So x is a n by the d dimensional matrix, and then d is a one dimensional matrix, and it's dependent upon the size of the data set. And then we're going to memorize the nearest neighbor, simply memorize all the training data, and then predict module is going to predict the labels for which the class, which label does it belong to, which class does it belong to. And so first module is going to memorize all the training data, and the other module predict function, it's going to we are going to perform iteration, and we're going to run for loop, and for each training image we are going to find the closest training image. It's going to compare the test image with the training image and see what similarities are there, and it's going to compute the neighbors, and then it's going to predict label, which label it's going to output the label, which class does it belong to. So how fast is it? So on a training time the complexity is going to be O of n, because we just learning labels, but when it comes to prediction the time complexity is O of n, which is not so good. And this classifiers performs bad when it comes to testing. This classifier performs badly when it comes to testing, because since this is going to make use of the training dataset as well to compute up with prediction labels, so this is just the opposite of what we want. We are gonna be testing our classifier on those devices which does not have more computational power, and we have memory constraint as well. So this classifier is not gonna do that. it's gonna be slow at the test time of training, but it's gonna be fast at prediction. So what does it look like? So if you see this image, you can see we have 5 classes over here, and each dot over here represents that image belongs to this class over here. So there are 5 classes over here. This is an example of multi-class classification, and as you can see we have this decision boundary over here, but it's not that sharp, it's not fluidic, and the reason why is because the distance metric which we are using, L1 Manhattan distance metric, it's coordinate dependent, so the edges are more sharp over here. And as you can see this dot, this area over here, so it's gonna be creating confusion for you because this Y yellow dot over here lies in the center of the green class, and it's not that robust when it comes to when you are using this data when you're going to be applying the classifier to other data sets. And that's why when we use k nearest neighbors, because we specify the number of classes which we want and then we take majority vote. So when we come across an image, we compute probabilities, we compute predictions, which class does it belong to and which label do we place it in, and then we compute majority vote and then we place it. So as you can see, the decision boundaries are more discrete over here, and it's very easily for us to distinguish between these classes. And this k over here is the hyperparameters which we have talked about earlier, in the earlier videos, and these are one of the main factors when it comes to training your classifiers, because there is no a particular process to decide which hyperparameter which are we going to use. So this white region over here just gives us an idea that there was no majority, there was like no nearest neighbor over here, and that the majority vote didn't count up to that. And so when we apply that and we evaluate it on the C14 dataset, we're gonna come up with something like this. So when we input an image over here, it's gonna compare it with other training images, and it's gonna compare features, it's gonna compute pixel wise distribution, and then it's gonna come up with similar images from the perspective of that classifier. But this algorithm may not be perfect at all because it makes several assumptions. And so there are 2 distance metrics which are commonly used. One is L1 distance and other one is called Euclidean distance. And if you see the locus I've drawn here for L1 distance, so it's a square with origin as a distance and turn 90 degree, and it's coordinate dependent. While on the other hand, L2 distance, if you draw the locus of it, you're gonna come up with this circle over here, and it's not coordinate dependent at all. And the reason why you wanna be like, before applying these metrics and testing which you wanna use, we're gonna talk about hyperparameters. And these are choices about the algorithm that we set rather to learn. So I've talked about hyperparameters in the Improving Neural Networks playlist, so feel free to check that out in order to get a broader understanding of what hyperparameters are all about. And these 2 distance metrics are example of that, and it's not fixed which distance metric are we gonna use, because it's so problem dependent that we are gonna test each one of them, and then we're gonna see how does it evaluate to our testing data set and which distance metric do we gonna go with. And there are no parameters in it, and hyperparameters are the main, they control how all these parameters are gonna change. And it's choosing hyperparameters is an empirical process. You test different hyperparameters and then we're gonna see which does the job well. For example, in case of neural networks, there are so many hyperparameters, number of hidden layers, learning rate, and all these parameters are decide how all your other parameters are gonna change. So having a good grip of deciding hyperparameters comes with years of experience. So I suggest you rather play with all these hyperparameters on your instance and let me know in the comment section below. I hope this gives you a better intuition of why do we use convolutional neural networks when it comes to image recognition, because all these classifiers don't work well because they are not so flexible and not so apt to use them in image recognition. So I've you will see a playlist of convolutional neural networks which I've talked about in detail and how you can implement in Keras using Python, and feel free to check it out. I hope this gives you a better intuition of how you can go about choosing which algorithm works well. Thank you for watching this video. Talk to you next one. Please.